So the method of initial rates, or the differential rate law, takes rate data and concentration data. So in that case, you have to record enough to think about how fast is it going as I'm looking at my concentrations. And slightly easier way a lot of times to collect data that is able to be used to think about the rate law is the integrated rate law. This works better for reactions with just one reactant, or at least that's what we'll be focusing on with our first sets of data. And we'll then see after some practice problems how it can be applied to multiple reactants. But the idea here is we're just looking at how that amount is changing per unit time instead of needing to calculate or measure a whole bunch of initial rates. So once again, we don't need the initial rates, but it's still about experiment. So the experiment is measuring the amount of reactant per unit time and graphing that concentration versus time. Because concentration is related to things like mass, to pH, to intensity of color, and to pressure, when we graph any of those things versus time, it would still be the integrated rate law, and we could interpret the graphs in the same way. We actually saw a few of these graphs when introducing the idea of reaction order. But a zero order reaction continues no matter how much of that reactant you have. So the rate is constant as that reactant goes away. Or if we were going to graph concentration versus time, we would find that it's a straight line until that chemical is gone. Although it seems unlikely that this could happen, many reactions are either zero order or have a component that is zero order. For a first order reaction, the rate's proportional to the concentration, which means it goes fastest when we have a lot of that chemical, but then it's going to form a curve. It's going to slow down. The rate slows down as the reaction goes away. So the concentration versus time is a curve, but we can analyze that graph to make it a straight line. If we're able to turn that curve into a straight line by looking at the natural log, then we can know that that is a first order reaction. We don't need to know the math behind this, nor be able to justify it beyond that. We're going to keep it simple and not even get into the explanation here in the video, although we could ask about it in class if curious. A second order reaction means that the speed or the rate is proportional to the square of the concentration. Something about the way that it reacts means that not just as it goes down, it slows down. As it goes down, it slows down exponentially or slows down extra. So concentration versus time is definitely a curve, but we can turn that curve into a straight line by graphing 1 over concentration. So as we come down here, we would see just what would these look like, zero, first, and second, if we did amount versus time. So concentration versus time would be a straight line until it ran out. The concentration versus time would be a curve here and would be a curve here. The difference in that curve may not be obvious as you're just looking at data or a graph on an AP question. The integrated rate law is what we are talking about, and it gives you some equations here of what would we have to do with this concentration data to make it linear. So right here, it's showing it as an exponential decay, but really that's a hard equation to kind of solve for some of our variables. So we often do it in the form where we have gotten rid of our exponent by looking at a natural log. So that's the connection right there. So with these equations, these are the equations of what we could do with our data to make the line straight. We said concentration versus time was straight kind of automatically or right away for zero order. So we just need to know the concentrations, and the slope in this case is negative K or the absolute value of K. So we've got that. Here, we would be graphing the natural log versus time. So right there, that would be our point slope form of our straight line. Maybe not point slope. Well, we've got the slope there and we've got points, so maybe. And then right here, that wasn't a straight line. but we made it straight by doing the reciprocal, or 1 over the concentrations. So when we plug in the concentrations there on the bottom, on the denominators, we can get this equation. And notice the slope is always related to k. And since k would always be positive, for the graphs with the negative slopes, it's the absolute value. Right here is the way the equations are given to you on the AP exam. So we do see a subtle difference from the way it was presented right there and there to what you would be given. So if we are doing a lab, we would be graphing our own data. We would graph concentration versus time. We would see if it's straight. If it's not, we would do some more things to it. In fact, just to be sure, we would almost always graph concentration versus time, natural log of concentration versus time, reciprocal of concentration versus time, and then we would analyze which is the straightest. Sometimes you can do that just by looking, but sometimes they all look kind of straight, and then we look to the R² value on our best fit line, and that tells us whichever one is closest to 1 is the straightest. On an AP question, they often just give you the graphs. We want them to be in this order: concentration, natural log, reciprocal, so that we can remember 0, 1, 2. And remember, 0 order is not only possible, it's fairly common. So that's why we start counting with 0, 0, 1, 2. But every now and then, they'll give us a set of data, and we need to understand how can that data be understood without needing to put it into a calculator, because maybe this will show up on a multiple choice, or maybe we don't have that much time on a free response. So 0 order not only is the easiest graph to understand, a straight line when we do concentration, it's also the easiest data to understand. The rate is constant, which means the concentration or amount drops the same amount each equal time interval. So every 10 seconds here, I went down by 1/10 of a molar. So that is a very clear, direct relationship that hopefully we could recognize, that time is evenly spaced, but so is the concentration. That's the definition of a straight line, which connects with 0 order. For first order, the rate is proportional to the concentrations, so it would end up as a curve, just like second order would. But something that's important here is that it is specifically an exponential decay, or that it has a constant half-life. So right here, half-life is something we try to spend some time on in Chem 1 when we're looking at atomic and nuclear, specifically nuclear reactions. The idea of how long it takes a reaction to cut its initial amount in half. That can be true for nuclear decays, or it can be true for a first order reaction. So every 20 seconds, if we look at this data, it goes to half as much as you started with. We went from 1 to 0.5 to 0.25. And if we came back up here, we could put dots on there. Well, I have a certain amount right there. A certain amount of time has passed, and the same amount of time will pass as I go to cut it in half again. So as I'm looking at that, it's not as easy or obvious, but it is a relationship that can be recognized by just looking at data instead of graphing it. Second order is harder to recognize by just looking at the data, but you can recognize it's not first order, it's not 0 order, it's not a straight line, there's no half-life. So that's how we can recognize it as second order. It's going to take some practice and repetition, but the key is 0 order is concentration versus time is straight. Natural log is straight for first order, reciprocal is straight, and they're in order on the periodic table equation sheet. The slope is related to k, although the k would always come out as positive. And lastly, right here, we use this equation. We could call that the half-life equation as a way to figure out and connect it to k, but only on an equation that has a constant half-life, which is a first-order reaction. So that guy's a little bit out of order because this only really applies to that equation right up there. But we'll practice and apply this with some practice problems.